Therefore, welcome to my talk entitled Fastcrash Making Learn Query Optimizer Hinting Effective. My name is Lukas. I'm with the Dresden Database Research Group at TU Dresden. And in our paper, we researched the questions on how can we use query optimizer hinting and how can we use machine learning to make query optimizer hinting even more effective. So first of all, we ask ourselves three questions. A, how to use query optimizer hinting. B, how should we learn hinting, or how should we model hinting with machine learning? And of course, does it help? So does it improve query performance? But let's start with the basics. So what is query optimizer hinting? Well, for that, I need to define three things. The first thing is a hint. A hint is a single parameter you can set your optimizer with. For example, on the right-hand side, you can see 3 hints, each setting a different kind of join. For example, here the hash join is switched to on. And the whole collection of these 3 hints is called a hint set. And this hint set is true or applicable for one single query. So the idea is you predict a hint set with some sort of oracle or all-knowing entity and forward this hint set to the database management system, to the optimizer, and then the optimizer gets steered with this hint set. So for example, we have this example query down here, which leads to this query execution plan. And now the question is, for the physical operator optimization, what kind of join do we need here? And we now have our oracle that tells us you should only use a hash join here. And so only the hash join is turned on. And we forward this, and then still the optimizer decides. It can still decide within all the optimization parameters it has, but because we have switched off the 2 other joins, it will decide to use a hash join for this join or for every join in this query, because it's the hint set scope is on a query and not on a single join. So the question then is, why should you do this? Why should you interfere with the query optimizer in such a way? Well, we did some experiments in our paper, and we used 6 hints, Boolean hints in Postgres, which leads to 64 hint sets. We used 3 benchmarks. I'm only presenting 2 here, the stack and the job benchmark. You will find the TPCH benchmark in the paper. And we used 2 systems, Postgres 12 and Postgres 14, because they are 2 completely different optimizers, because there were major changes between those 2 versions of Postgres. And we've noticed, if you find the optimal hint set, so if you have this all-knowing oracle that tells you the perfect hint set for every query, you get a speed up for all the queries. You can see here on the x-axis the queries and their speed up if you hint them with the optimal hint set. This is done for the stack benchmark here on Postgres 12. And you can also see that the tail queries, the blue ones, get the most speed up. So the long-running queries get the most speed up. So we also did this for the job and for PG14. So you get this matrix of plots. And you can see in all cases, there is a speed up larger than 1 for nearly all the queries. So hinting is definitely beneficial for query runtimes, especially compared to the Postgres default. So why should we then use machine learning for that? Well, with our experiments, we also tracked what kind of hint set are occurring as an optimal hint set. So you can see here the enumeration of the hint sets. We use the binary encoding of the hint set just as a number. So this is, for example, hint set number 20. One special hint set is the hint set number 63. This is the Postgres default hint set. So if you install a fresh Postgres, this will be the configuration that Postgres is using. But you can see here for, again, Postgres 12 and stack, there is no general pattern. And we confirmed this for several other runs with the job benchmark and both benchmarks on Postgres 14. And you can see from benchmark to benchmark and between systems, there is no general pattern. So finding the optimal hint set is not straightforward. And if you have problems finding rules for finding something or for classifying something, predicting something, then you should use, of course, machine learning. But how should you learn it? So what's the idea behind learned hinting, and what's the speciality of our approach? Well, first of all, our approach is called FastGRESS. And FastGRESS uses a local model approach, which uses divide and conquer. But first of all, let me show you an example. This is our example query from the beginning of our slides. And you need now two components. The first is the DBMS, of course, and the second one is our FastGRESS component, which is completely decoupled from the database management system, as you see. The first thing FastGRESS is doing is it uses the information of the joint tables, RNT in our case here, to select a certain context. So the FastGRESS knows that only information regarding the joint RT are now important. And the information regarding these joints are all the predicates. So we take all the predicates and encode them in a certain way. And then we train a gradient boosting model, which is specialized on this context, on this small subproblem of the whole possibility of all the possible joint combinations and queries that there are. And this model is then able to directly predict a hint set. You remember from the first, or from one of the first slides, that we have to enable the hash join and we have to disable the two other joins. And you can see this is exactly what the model is predicting, this bit vector. Then we transform it to the SQL statement, also from the beginning of this talk, and forward it to the database management system. The management system is now hinted with these 3 hints, or with this one hint set. And now we can run the query. And now the optimizer will only take hash joins because we basically told the optimizer to only use hash joins. So what is the local model approach? Well, this is the whole FastGRESS architecture. You can see every query comes into the system, and then the joins are analyzed, so you can map it to a certain context. There are several contexts, one for each combination of joint queries, and then you take the predicates, put it into the specialized featurization, which is really special or specialized for the context, and also a model. You do not need to have to use gradient boosting. You can use any other model, but this model then directly predicts a hint set, and this hint set is then forwarded to the DBMS. Then the query is executed, and we also measure runtimes to get some information to retrain FastGRESS if the model, so this particular model here, grows stale. So what are the advantages of this approach compared to, for example, one large model? Well, first of all, we can directly predict a hint set for a certain context. So we specialize our models to a certain context, and we can directly predict the hint set, of course. Because we're focusing on just context, we can reduce the complexity of this model. So these models are much, much smaller than comparable neural networks, which would model all the contexts as one, which most other approaches do. And of course, we do not need any additional planner calls. We have better quality. We have faster training and faster model application because these models are less complex and therefore can specialize or concentrate their whole expressiveness within this context. So one thing that is missing now is this retraining part here. So how can we make sure that if the workload of the data is shifting, that the models get retrained during runtime? And we implemented a component that is called runtime model maintenance or retraining. And this basically looks at critical queries. And a critical queries is, in our definition, a long-running query, so a query that runs longer than the expected average. due to a badly predicted hint set. So the model predicted a wrong hint set, and therefore the query is running too long. And the major idea is, if I notice such a query, then we should include this query into the training data to learn this problematic query or this critical query. And the naive approach would be to retrain after every new query, which isn't feasible because this would stress the model or the hardware where the model is trained unnecessarily. So we only retrain when it's necessary. But for that, we need to define a threshold for when necessary. And we therefore define this threshold as a part of a timeout with relative parts and absolute parts. So you have this equation here, which is basically the maximum between a defined absolute timeout after 20 seconds, for example. You definitely want to have your query finished, and a percentile of all the current runtimes in your context. So we store all the runtimes within a context for all query runtimes within a context, and take then the defined relative percentile of those runtimes, and together with the absolute part, we build this threshold. So whenever a query exceeds this threshold, then a retraining is triggered. And a retraining is also only triggered context-wise, so we do not retrain all the models, but only one model is retrained. All the other models can work as they are, and so you do not block the query execution, because you can't get predictions from the model that is currently retraining, because you're only retraining one model at a time for one context. So does it help? Is it beneficial to use hinting? So I will show you some plots from our evaluation. These are not all plots, but I think these are the most important ones. So first of all, this is again the results for Stack on Postgres 12. And you can see two lines. The black line down here is the baseline, so basically the standard Postgres performance. And from our previous experiments, we know that if we hint every query with the optimal hint set, we reach this speed up of 2.5. This is the red line. We also compared ourselves with the competitor, which is Bao, and you can see it approximately reaches a speed up of 1.2 for the whole workload. Note that the x-axis is the split of the data in training and test data. So here, for example, for the first part, we use 10% of the benchmark, the Stack benchmark for training, and 90% for testing, meaning the model does not see 90% of all queries. These are completely unknown. We only predict on them. We do not train with them. And you can see without a retraining component, we get a speed up of 1.6, and then the speed up increases until it reaches optimal performance. And if we enable this intelligent retraining I've shown with the critical query detection, we you see we start with already a speed up of 2.0, and you can also see that the number of critical queries, of course, decreases. This is mainly due to the fact that less critical queries occur because we learn better predictions for every query, including critical queries. And of course, this does not only work on Stack with Postgres 14. This works with a different system, Stack on Postgres 14, and with different workloads. For example, here the job on Postgres 14 again. And you can see similar results. We're always getting better speedups. Note that Bao is only available for Postgres 12. There is no version for Postgres 14, so we only could compare our results to Bao on Postgres 12. So to summarize, we had these three questions, and I hope I could answer them, because we think that Query Optimizer hinting is a very powerful tool to improve query performance without deep integration into the Query Optimizer, because you can use external knowledge and external components to predict the right hint set and then just steer the optimizer. I've presented FastCREST, our local model approach, with this context-wise prediction of hint sets with no deep integration. It's a Python component you can use with any DBMS that exposes hints to the user. And we have this special retraining component that helps you avoid the staleness of models during data or workload shifts. And I've shown you that it improves performance both regarding the competition, and it also beats the Postgres default. So with this, I'm at the end of my talk. I hope I could convince you that hinting is important, or query optimizer hinting is important, and that machine learning or learned query optimizer hinting is a benefit for query performance optimization.